Hi everyone, my name is Nick. I'm an engineer on the TensorBoard team, and I'm here today to talk about TensorBoard and summaries. So first off, just an outline of what I'll be talking about. First, I'll give an overview of TensorBoard, what it is and how it works, just mostly sort of as background. Then I'll talk for a bit about the tf.Summary APIs, in particular sort of how they've evolved from TF 1.x to TF 2.0. And then finally, I'll talk a little bit about the summary data format, log directories, event files, some best practices, and tips. So let's go ahead and get started. So TensorBoard. Hopefully, most of you have heard of TensorBoard. If you haven't, it's the visualization toolkit for TensorFlow. That's a picture of the web UI on the right. Typically, you run this from the command line as the TensorBoard command. It prints out a URL, you view it in your browser, and from there on, you have a bunch of different controls and visualizations. And the sort of key selling point of TensorBoard is that it provides cool visualizations out of the box without a lot of extra work. You basically can just run it on your data and get a bunch of different kinds of sort of tools and different sort of analyses you can do. So let's dive into the sort of parts of TensorBoard from the user perspective a little bit. First off, there's multiple dashboards. So we have this sort of tab set up with dashboards across the top. The screenshot shows the scalars dashboard, which is kind of the default one. But there's also dashboards for images, histograms, graphs, a whole bunch. More are being added every month almost. And one thing that many of the dashboards have in common is this ability to sort of slice and dice your data by run and by tag. And a run, you can think of that as kind of a run of your TensorFlow program or your TensorFlow job. And a tag corresponds to like a specific named metric or sort of piece of summary data. So here, the runs, we have a train and eval run on the lower left corner in the run selector. And then we have different tags, including the cross-entropy tag is the one being visualized. And one more thing I'll mention is that one thing a lot of TensorBoard emphasizes is seeing how your data changes over time. So most of the data takes the form of a time series. And in this case, with the scalars dashboard, the time series is sort of a step count across the x-axis. So we might ask, what's going on behind the scenes to make this all come together? And so here's our sort of architecture diagram for TensorBoard. We'll start over on the left with your TensorFlow job. It writes data to disk using the tf.Summary API. And we'll talk both about the summary API and the sort of event file format a little more later. Then the center component is TensorBoard itself. We have a background thread that loads event file data, and because the event file data itself isn't efficient for querying, we sort of construct a subsample of the data in memory that we can query more efficiently. And then the rest of TensorBoard is a web server that has sort of a plugin architecture. So each dashboard on the front end as a backend, it has a specific plugin backend. So for example, the scalars dashboard talks to a scalars backend, images to an image backend. And this allows the backends to do sort of pre-processing or otherwise structure the data in an appropriate way for the front end to display. And then each plugin has a front-end dashboard component, which are all sort of compiled together by TensorBoard and served as a single page in index.html. And that page communicates back and forth with the backends through standard HTTP requests. And then finally, hopefully, we have our happy user on the other end, seeing their data, analyzing it, getting useful insights. And I'll talk a little more about just some details about the front end. The front end is built on the Polymer Web Component Framework, where you define custom elements. So the entirety of TensorBoard is one large custom element, TF TensorBoard. But that's just the top. From there on, each plugin front end is like each dashboard is its own front end component. For example, there's a TF scalar dashboard. And then all the way down to shared components for sort of more basic UI elements. So we can think of these as like a button or a selector or like a card element or a collapsible pane. And these components are shared across many of the dashboards, and that's one of the key ways in which TensorBoard achieves what is hopefully a somewhat uniform look and feel from dashboard to dashboard. The actual logic for these components is implemented in JavaScript. Some of that's actually TypeScript that we compile to JavaScript. Especially the more complicated visualizations, TypeScript helps sort of build them up as libraries without having to worry about some of the pitfalls you might get writing them in pure JavaScript. And then the actual visualizations are sort of a mix of different implementations. Many of them use Plottable, which is a wrapper library over the D3, the standard JavaScript visualization library. Some of them use native D3. And then for some of the more complex visualizations, there are libraries that do some of the heavy lifting. So the graph visualization, for example, uses a directed graph library to do layout. The projector uses a sort of WebGL wrapper library to do the 3D visualizations. And the recently introduced What If Tool plugin uses the facets library from Pair folks. So we sort of bring a whole bunch of different visualization technologies together under one sort of TensorBoard umbrella, is how you can think about the front end. So now that we have sort of an overview of TensorBoard itself, I'll talk about how your data actually gets to TensorBoard. So how do you unlock all of this functionality? And the spoiler announcement to that is the tf.Summary API. So to summarize the Summary API, you can think of it as structured logging for your model. The goal is really to make it easy to instrument your model code. So to allow you to log metrics, weights, details about predictions, input data, performance metrics, pretty much anything that you might want to instrument. And you can log these all, save them to disk for later analysis. And you won't necessarily always be calling the Summary API directly. Some frameworks call the Summary API for you. So for example, Estimator has the Summary saver hook. Keras has a TensorBoard callback, which takes care of some of the sort of nitty-gritty. But underlying that is still the Summary API. So most data gets to TensorBoard in this way. There are some exceptions. Some dashboards have different sort of data flows. The debugger is a good example of this. The debugger dashboard integrates with tf.Debug. It has sort of a separate back channel that it uses to communicate information. It doesn't use the Summary API. But many of the commonly used dashboards do. And so the Summary API is actually has sort of, there's several variations. And when talking about the variations, it's useful to think of the API as having two basic halves. On one half, we have sort of the instrumentation surface. So these are like logging ops that you place in your model code. They're pretty familiar to people who've used the Summary API, things like scalar, histogram, image. And then the other half of the Summary API is about writing that log data to disk and sort of creating the specially formatted log file, which TensorBoard can read and extract the data from. And so just to sort of give a sense of how those relate to the different versions, there's 4 variations of the Summary API from TF 1.x to 2.0. And the sort of 2 key dimensions on which they vary are kind of the instrumentation side and the writing side. And we'll go into this in more detail. But first off, let's start with the sort of most familiar Summary API from TF 1.x. So just sort of as a review, again, if you've used the Summary API before, this will look familiar. But this is kind of a code sample of using the Summary API in 1.x. The instrumentation ops like scalar actually output Summary protos directly. Then those are merged together by a merge all op that generates a combined proto output. The combined output you can fetch using session.run. And then that output you can write to a file writer for a particular log directory using this sort of add summary call that takes the summary proto itself and also a step. So this is, in a nutshell, the sort of flow for TF 1.x summary writing. There's some limitations to this, which I'll describe in 2 parts. The first set of limitations has to do with the kinds of data types that we can support. So in TF 1.x, there's a fixed set of data types. And adding new ones is a little involved. It requires changes to TensorFlow in terms of you would need a new proto definition field, you'd need a new op definition, a new kernel, and like a new Python API symbol. And this is sort of a barrier to extensibility for adding new data types to support new TensorBoard plugins. It's led people to do sort of creative workarounds, for example, like rendering a matplotlib plot in your training code and then logging it as an image summary. And the prompt here is, what if we instead had sort of a single op or a set of ops that could generalize across data formats? And this brings us to our first sort of variation, which is the TensorBoard Summary API, where we try and make this extensible to new data types. And the TensorBoard.Summary API, the mechanism here is that we use the tensor itself as a generic data container, which can correspond to, for example, we can represent a histogram, an image, a scalar itself. We can represent these all in certain formats as tensors. And what this lets us do is use a shared TensorSummary API with some metadata that we can use to describe the tensor format for our sort of one place to send summary data. And so TensorBoard.Summary, the principle it takes is actually that you can re-implement the tf.Summary ops and APIs as Python logic to call TensorFlow ops for sort of pre-processing and then a call to TensorSummary. And this is a win in the sense that you no longer need individual C++ kernels and protofields for each individual data type. So the TensorBoard plugins today actually do this. They have for a while. They have their own summary ops defined in TensorBoard. And the result of this has been that for new TensorBoard plugins, where this is the only option, there's been quite a bit of uptake. For example, the PR curve plugin has a PR curve summary, and that's the main route people use. But for existing data types, there isn't really much reason to stop using tf.Summary. And so for those, it makes sense, that's been what people have used. But then tf.Summary, it still has some other limitations. And so that's what we're going to look at next. So the second set of limitations in tf.Summary is sort of around this requirement that the summary data flows through the graph itself. So merge all uses this hidden graph collection essentially to achieve the effect to the user as though your summary ops have side effects of writing data, kind of like a conventional, the way you use a standard logging API. But because it's using a graph collection, it's not really safe for use inside control flow and functions. And also with eager execution, it's very cumbersome to use. You would sort of have to keep track of the outputs by hand or in some way wait to send them to the writer. And these limitations also apply to TensorBoard.Summary ops themselves because they don't really change anything about the writing structure. And these limitations have sort of led to the prompt of, what about if summary recording was an actual side effect of op execution? And so this brings us to tf.Contrib.Summary, which has new writing logic that achieves this. And so here's a code sample for tf.Contrib.Summary, which looks pretty different from the original tf.Summary. It works with eager execution, but as sort of the change we have to make is now we create a writer up front via create file writer. It's still tied to a specific log directory, which we'll talk more about later. You set the writer as sort of the default writer in the context. You enable summary recording. And then the individual instrumentation ops will actually write directly to the writer when they run. So this gives you sort of standard usage pattern of a logging API that you would expect. And it's compatible with eager execution and also with graph execution. So some details to how this works with contrib summaries. The writer is backed in the TensorFlow runtime by a C++ resource called Summary Writer Interface. That essentially encapsulates the actual writing logic, which makes it possible in principle to have different implementations of this. The default writer, as sort of conceived of by the Python code that's executing, is just a handle to that resource stored in the context. And then instrumentation ops like scalar and image now are stateful ops. They have side effects, and they achieve this by taking the default writer handle as input along with the data they're supposed to write. and then the actual op kernel implements the writing using the C++ resource object. And with this model, the Python writer objects mostly manage this state. They don't quite completely align because the C++ resource could actually be shared across Python objects, which is a little bit different still from the TensorFlow 2.0 paradigm, where we want our sort of Python state to reflect runtime state one-to-one. And this was just one example of a few things that we're changing with TF 2.0. And with TF 2.0, we had this opportunity to sort of stitch some of these features together and make sort of one unified new tf.Summary API. And so here we sort of are completing our filling out of the space of possibilities, where we have the tf.Summary API bringing together features from really all three of the existing APIs in 2.0. So tf.Summary and TF 2.0, it really represents, like I said, this unification of the three different APIs. The instrumentation ops are actually provided by TensorBoard, and they use this generic tensor data format that's the same format as TensorBoard.Summary, which lets them extend to multiple different kinds of data types. We borrowed the sort of implementation of the writing logic from tf.Contrib.Summary and some of the APIs, but with slightly adjusted semantics in some places, mostly just so that we align with the sort of state management in TF 2.0. And then there's actually a not trivial amount of just sort of glue and circular import fixes to get the two halves of both TensorBoard and the original TF summary writing API to talk to each other. And I'll go into a little bit more detail about that. So the dependency structure for tf.Summary and TF 2.0 is a little bit complicated. The actual Python module contains API symbols from both TensorBoard and TensorFlow fused together. But because the TensorBoard symbols also depend on TensorFlow, sort of this creates this complicated dependency relationship. And the way we sort of linearize this dependency relationship is that TensorFlow.Summary or TF.Summary in the original TensorFlow code exposes the writing APIs, like create file writer and the sort of actual underlying writing logic. Then we have what I kind of call a shim module in TensorBoard that merges those symbols via a wildcard import with the regular imports of the instrumentation APIs like scalar and image that are now defined in TensorBoard. And this produces sort of the combined namespace, but now it's a TensorBoard module. So then TensorFlow in its sort of top level init.py, where it's assembling the API together, imports the TensorBoard module and sets that as the new tf.Summary. And this does mean that the API surface depends sort of directly on TensorBoard, but TensorFlow already has a pip dependency on TensorBoard, so this isn't really a change in that respect. But the API surface is now sort of being constructed through multiple components, where the summary component is provided by TensorBoard. And what that gives us is a single module that combines both sets of symbols. So the delta for users is smaller, but we can sort of have the code live in the appropriate places for now. And so these are some code samples for the TF 2.0 summary API. The first one shows it under eager execution. It should look fairly similar to Contrib. You create the writer up front, set it as default. You can call the instrumentation ops directly, so you no longer need to enable summary writing, which makes it a little more streamlined. And I should say that the ops, they write when executed sort of in theory, but there's actually some buffering in the writer. So usually you want to make sure to flush the writer to ensure the data is actually written to disk. And this example shows an explicit flush. That in eager, it will do flushing for you when you exit the as default context, but it's good if you sort of care about making sure, like for example, after every iteration of the loop that you have data persisted to disk, it's good to flush the writer. And then this is an example with the @tf function decorator. Again, you create the writer up front. One important thing to note here is that the writer you have to maintain a reference to it as long as you have a function that uses the writer. And this has to do with the sort of difference between when the function is traced and executed. It's a limitation that hopefully we can sort of improve this a little bit, but for now at least that's one caveat. So the best way to sort of handle that is you set the writer as default in the function itself, and then call the instrumentation ops that you need. And these write, again, when executed, meaning when the function is actually called. So we can see that's happening down with the myfunc call. And then you can flush the writer again. And then here we have an example with sort of legacy graph execution, since there's still folks who use that in 2.0. This is a little bit more verbose, but again, you create the writer, you set it as default, you've sort of constructed your graph, and then in this case, you need to explicitly initialize the writer via running the init op. We have kind of a compatibility shim that lets you run all of the v2 summary ops so that you don't have to keep track of them manually. And then, again, flushing the writer. So these are the sort of, this is how you would use it in legacy graph execution. So how do you get to TF 2.0? The contrib summary API is close enough to the 2.0 summary API that we do some actually mostly we auto-migrate this in the TF upgrade v2 migration script. But tf.Summary in 1.0 is sufficiently different on the writing side that we can't really do a safe auto-migration. So here's the kind of 3-bullet version of how to migrate by hand. The first thing is that the writer now needs to be sort of present, created, and set via as default before using the summary ops. And this is a limitation that, it's a little bit tricky. We're hoping to sort of relax this a little bit so it's possible to set a writer later. But for now, you want to have the default writer already present. Otherwise, the summary ops basically just become no ops if there's no writer, since they have nowhere to write to. Then each op takes its own step argument now. This is because since there's no sort of later step where you add the summary to the writer, that's where the step was previously provided. And there's also no global step in TF 2.0, so there isn't really a good default variable to use. So for now, steps are being passed explicitly, and I'll talk about this a little more later on the next slide. And then the function signatures for the instrumentation ops like scalar and image have changed slightly. The most obvious thing being that they'd no longer return an output because they write via side effect, but also there's slight differences in the keyword arguments that won't affect most people, but it's something good to know about. And these details will all be in the external migration guide soon. And so the other changes, and this is some of the other stuff I was mentioning, one change is with graph writing. Since there's no sort of default global graph in 2.0, there's no direct instrumentation op to write the graph. Instead, the approach here is there's a set of sort of tracing style APIs to enable and disable tracing. And what those do is they record the graphs of executing TF functions, so functions that execute while the tracing is enabled, to the summary writer. And this sort of better reflects the TF 2.0 understanding of graphs as something that are associated with functions as they execute. Then this is sort of kind of what I was alluding to. It's still a little bit tricky to use default writers with graph mode, since it's not always the case that you know which writer you want to use as you're assembling the graph. So we're working on making that a little bit more user-friendly. And setting the step for each op is also definitely boilerplate. So that's another area where we're looking to make it possible to set the step, maybe in one place or somehow in the context to avoid the need to pass it into ops individually. And then the event file binary representation has changed. This only affects you. This doesn't affect TensorBoard in that TensorBoard already supports this format. But if you were parsing event files in any manual way, you might notice this change. And I'll talk a little bit more about that change in the next section. And finally, as mentioned, the writers now have sort of a one-to-one mapping to the underlying resource and event file. So there's no more sharing of sort of writer resources. OK, and then the last section will be about the summary data format. So this is log directories, event files, how your data is actually sort of persisted. So first off, what is a log directory? The TensorBoard command expects a required --logdir flag. In fact, your first introduction to TensorBoard may have been trying to run it, and then it spits out an error that you didn't pass the logdir flag. So the log directory flag is the location that TensorBoard expects to read data from. And this is often sort of the primary output directory for a TensorFlow program. Frameworks, again, like Estimator and Keras, have different knobs for where output goes, but often people will put it all sort of under one root directory, and that's often what people use as the log directory. But TensorBoard has sort of this flexible interpretation where really all it cares about is that it's a directory tree containing summary data. And when I say directory tree, I really do mean a tree because the data can be arbitrarily deep. TensorBoard will traverse the entire tree looking for summary data. And you might think that could sort of be a problem sometimes, especially if there's hundreds, thousands of event files. And it's true, yeah, log directories can be pretty large. And so TensorBoard tries to sort of take advantage of structure in the log directory by mapping subdirectories of the logdir to this notion of runs, which we talked about a little bit in the early section about the TensorBoard UI. So again, these are runs like a run of a program, they're not individual session.run calls. And when TensorBoard loads a run, the sort of definition it uses is that it's any directory in the logdir that has at least one event file in it. And in this case, we mean only direct children. So the directory has to contain an actual event file. And an event file is just defined as a file that has the string tf events in the name, which is just the standard naming convention used by summary writers. So as an example of this, we have this log directory structure, which has sort of a root directory logs. It has two experiment subdirectories in it. The first experiment contains an event file, so that makes that itself a run. It also contains two sort of subdirectories, train and eval, with event files. So those two also become runs. They're sort of, visually they look like subruns, but they're all considered independent runs for TensorBoard, at least in the current interpretation. And then in experiment 2, that doesn't contain an event file directly, so it's not a run, but it has a train sort of subdirectory under it. So TensorBoard looks at this log directory and traverses it and finds 4 different runs. And this traversal step happens continuously. TensorBoard will pull the log directory for new data, and this is to facilitate using TensorBoard sort of as a way to monitor the progress of a running job, or even potentially a job that hasn't started yet. You might start TensorBoard and your job at the same time, so this directory may not even exist yet. And we may expect that different runs will be created as it proceeds. So we need to continuously check for new directories being created, new data being appended. In the case where you know that your data is not changing, like you're just viewing old data, you can disable this using the reload interval flag. And you can also adjust the interval at which it pulls. So when it's traversing the log directory, it does this in 2 passes. The first pass is finding new runs. So it searches the directory tree for new directories with tf event files in them. This can be very expensive if your tree is deeply nested, and especially if it's on a remote file system, and especially if the remote file system is on a different continent, which I've seen sometimes. So a key here is that walking the whole directory tree can be pretty slow. We have some optimizations for this. So for example, on Google Cloud Storage, we take it, rather than walking each directory individually, we have this sort of iterative globbing approach, which we basically use to find all directories at a given depth at the same time, which takes advantage of the fact that GCS doesn't actually really have directories. There's sort of an illusion. And there's other sort of file system optimizations like this that we would like to make as well. But that's just one example. And then the second pass, after it's found all the new runs, is that it reads new event file data from each run. And it goes through the runs essentially in series. There's sort of a limiting factor in Python itself for parallelizing this, but again, something that we are interested in working on improving. And then when you actually have the set of event files for a run, TensorBoard iterates over them basically in directory listing order. You might have noticed on the previous slide with the example logdir that the event files all have like a fixed prefix and then a timestamp. And so what this means is that the directory order is essentially creation order of the event files. And so in each event file, we read records from it sequentially until we get to the end of the file. And then at that point, TensorBoard checks to see if there's a subsequent file already created. If so, it continues to that one. Otherwise, it says, OK, I'm done with this run, and then it goes to the next run. And after it finishes all the runs, it waits for the reload interval, and then it starts a new reload cycle. And this reload resumes the read from the same offset in every file per run that it stopped in. And an important sort of thing to point out here is that TensorBoard won't ever revisit an earlier file within a run. So if it finishes reading a file and continues to a later one, it won't ever go back to check if the previous file contains new data. And this is based on the assumption that the last file is the only active one, the only one being actively written to. And it's important to avoid sort of checking all event files, which can be, sometimes there's thousands of event files in a single run directory. And so that's a sort of mechanism for avoiding wasted rechecking. But this assumption definitely doesn't always hold. There are cases when a single program is using multiple active writers within a run. And in that case, it can seem like the data is being skipped because you proceed to a new file and the data added to the original file no longer appears in TensorBoard. And luckily, it's fairly straightforward to work around this. You just restart TensorBoard, and it will always pick up all the data that existed at the time it started. But we're working on a better fix for this so that we can still detect and read when there's data added to files other than the last one. But this is something that has bitten people before, so just a heads up. And then, so the actual event file format, this is based on tf.Record, which is this sort of standard TensorFlow format. It's the same as tf.io, tf.Record writer. And it's a pretty simple format, enough that it fits on the left side of this slide. It's basically just a bunch of binary strings prefixed by their length with CRCs for data integrity. And one particular thing that I'll note is that because there's no sort of specific length for each string, there's no real way to seek ahead in the file. You basically have to read it sequentially. And there's also no built-in compression of any kind. And TensorBoard, it's possible in theory to have the whole file be compressed. TensorBoard doesn't support this yet, but it's something that could help save space when there's a lot of redundant, strings within the event file. And then each individual record, so tf.Record is sort of the framing structure for the event file. Each individual record is a serialized event protocol buffer. And this sort of simplified schema for the protocol buffer is shown on the left. We have a wall time and a step, which are used to construct the time series. And then we have a few different ways to store data. But the primary one is a summary submessage. The main exception is graph data gets stored in the graph.def separately. And then we can look at the summary submessage, which is itself basically a list of value submessages. That's where the actual interesting part is. And each one of these contains a tag. Again, that's from sort of our overview of the UI. That's like the name or ID of the summary as shown in TensorBoard. We have metadata, which is used to describe the more generic tensor formats, and then specific type fields, including ones for the original tf1.x, sort of specific fields for each type, and then the tensor field, which can be used with the new sort of new tensor style instrumentation ops to hold sort of general forms of data. And then in terms of loading the summary data into memory, so I mentioned this briefly in the sort of architecture stage, but TensorBoard has to load the summary data into memory because, like I said, there's no real indexing or random access in the event file. You can think of them like they're just like raw logs. And so TensorBoard loads it into memory and creates sort of its own indexes of data by run, plugin, and tag, which support the different kinds of visualization queries that plugins need. And TensorBoard also does downsampling in order to avoid running out of memory, since the log directory may contain far more data than could reasonably fit in TensorBoard's RAM. And to do the downsampling, it uses a reservoir sampling algorithm. It's essentially just an algorithm for uniform sampling when you don't know the size of your sequence in advance, which is the case when we're sort of consuming data from an active job. And because of this, it has sort of a random aspect, which can be surprising to users, where you might not understand, like, why is this step being taken and not this one, and there's like a gap between steps. This can be tuned with a samples per plugin flag, so that tunes the size of the reservoir. Basically, if you make the reservoir larger than your total number of steps, you'll always see all of your data. So that gives you a certain amount of control over how that sampling works. And just to sort of review some of this section, there's some best practices for, at least in the current TensorBoard, how to get sort of the best performance. One of the basic ones is just to avoid having enormous log directories in terms of the number of files, subdirectories, quantity of data. This doesn't actually mean that the sort of overall log directory has to be small. It just means that TensorBoard itself will run better if you can launch it at a directory that just contains relevant data for what you want to examine. So sort of a hierarchical structure where you can pick sort of an experiment subdirectory or group a few experiments together works really well here. I mentioned the reload interval. You can set it to 0 to disable reload. So for unchanging data, this helps avoid sort of extra overhead. And that's especially useful on a remote file system case. In that case, it's also useful if you can run TensorBoard close to your data or sort of download a subset of it that you need so that it doesn't all have to be fetched over the network. And for now, due to the sort of way that superseded event files aren't reread, it's best to avoid multiple active writers pointed at the same directory. This is something, again, that we're actively working on improving this, but at least for now, that can lead to sort of the appearance that some data gets skipped. And then in general, stay tuned for log-dir performance improvements. We're hoping to make a number of these improvements soon. And that pretty much rounds out the content that I have for today. So I'd like to thank everybody for attending. And if you want to find out more about TensorBoard, we have a new sort of subsite on tensorflow.org/TensorBoard. You can also find us on GitHub, and people interested in contributing are welcome to join the TensorBoard Special Interest Group. Thank you all very much.
What are the potential use cases for the multiple summary writers?
The potential use cases for the multiple summary writers, sometimes this is just sort of a matter of code structure, or sort of if you're using a library that itself creates a summary writer. It's not always straightforward to ensure that you can use the same writer. I mean, because it's different. So TF1.x had this file writer cache, which was sort of the best practice then was to use this sort of shared cache to ensure you only had one writer per directory, and it was to work around this problem. I think it's better to work around it on the TensorBoard side and have some ideas for how to do that. So hopefully that part will be out of date soon, like within a month or two.
Are there plans to change the event file format?
Yeah, so I think a lot of this depends on, I think that the event file format itself could be a lot more, it could be a lot better tailored to what TensorBoard actually needs. And I mean, some of the things I mentioned would just be like, even if we had an index into the event file, that could potentially help we could potentially parallelize reads, or we could sort of scan ahead and do sort of like smarter sampling. Like rather than reading all the data and then downsampling it, we could just like pick different offsets and sample from there. We're constrained right now mostly by this being kind of the legacy format. But I think it would be pretty interesting to explore new formats. Something, particularly when you have different data types mixed in, something sort of columnar could be kind of useful, where you can like read only images if you sort of need to read images, or sort of otherwise avoid the phenomenon where, so this happens sometimes where like one particular event file contains like lots and lots of large images or large graph defs. And this sort of blocks the reading of like a lot of small scalar data, and that's obviously not really, it doesn't really make sense. But again, it's a sort of limitation of having the data only be accessible sequentially.
Can you talk a little bit more about the graph dashboard? Like, is graph just another summary, or how does?
Yeah, so graph is the graph visualization, which was actually originally created by Big Picture. It's a visualization of the actual TensorFlow graph, so like the computation graph with ops and edges connecting them and sort of the data flow. It's pretty cool. It's really a good way to sort of, if you want to sort of visually understand what's going on. It works best when the code has sort of uses like scoping to kind of delineate different parts of the model. If it's just sort of a giant soup of ops, it's a little hard to like understand the higher order structure. And there's actually some cool work done for TF 2.0, which isn't in the presentation, about for Keras showing sort of the Keras conceptual graph using Keras layers to give you sort of a better view into the kind of high-level structure of the model like you'd expect to see, in a diagram written by a human. But the graph dashboard can still be useful for sort of understanding exactly what ops are happening, and sometimes it's useful for debugging cases if some sort of part of the graph is behaving weirdly. Maybe you didn't realize that you actually have like an edge between two different ops that was unexpected.
Are there any plans to add support for basically like that sort of higher order structure annotation? So I'm imagining, for instance, like if you have ResNet, having like the whole model and then a block and then a sub-block and sort of, there's like 5 layers of structural depth that would be nice to be able to annotate.
Yeah, I think this is an interesting question. I think, so right now the main tool you have for that structure is just sort of name scoping, but it only really works if the part of the graph is all being defined in the same place anyway. I think it would be really nice to have the graph visualization support more kind of strategies for human-friendly annotation and organization. I think the recent work that we've done on this has been the Keras conceptual graph, which Stefan did over there. But I think having that work for not just Keras layers, but sort of more general like model decomposition approaches would be really nice.
And, like often I find that the problem isn't that it's not capturing enough, it's actually that it's capturing too much. So for instance, like you'll have like a convolution, but then there's a bunch of like loss and regularization, and there winds up being a bunch of tensors that sort of clutter. And so actually even the ability to like filter stuff out of the conceptual graph would also be.
So there is, there's like a feature in the graph dashboard where you can sort of remove nodes from the main graph, but I believe the only way that has to kind of be done by hand. It does like a certain amount of like automatic extraction of things that are sort of less important out of the graph. But so maybe that's a place we could look into having like either sort of a smarter procedure for doing that, or a way to sort of tag like, hey, this section of like, I don't actually want to see any of these, or like this sort of should be factored out in some way. Yeah, thanks.